Hi, welcome to the ComSci 137 lecture. Sunny here. For this module, we'll be discussing about the Internet Protocol. Let's start. Here is the diagram that shows how the network layer interacts with the lower layer protocol in a network. Here are the diagrams on how the network layer works at the source, at the destination, and at the router. The Internet at the network layer uses the datagram approach to packet switching. It uses the universal address defined in the network layer to route packets from the source to the destination. The communication is connectionless and it treats each packet independently. The network layer in version 4 can be thought of as one main protocol and three auxiliary ones. The main protocol, the Internet Protocol version 4, is responsible for packetizing, forwarding, and delivery of a packet at the network layer. Here is the position of IP and the other network layer protocols in TCP/IP protocol suite. Packets used by the IP are called datagrams. Here shows the IPv4 datagram format. A datagram is a variable length packet consisting of two parts, header and payload. The header is 20 to 60 bytes in length and contains information essential to routing and delivery. It is customary in TCP/IP to show the header in 4-byte sections. The 4-bit version number field defines the version of the IPv4 protocol, which obviously has the value of 4. The 4-bit header length field defines the total length of the datagram header in 4-byte words. The IPv4 datagram has a variable length header. When a device receives a datagram, it needs to know when the header stops and the data, which is encapsulated in the packet, starts. For the service field, in the original design of the IP header, this field was referred to as type of service, which defined how the datagram should be handled. In the late 1990s, IETF redefined the field to provide differentiated services. Precedence is a 3-bit subfield of the service type field that defines the priority of datagram in issues such as congestion. The type of service bits is a 4-bit subfield with each bit having a special meaning like normal, minimize cost, maximize reliability, maximize throughput, and minimize delay. Here are some of the service types of some applications. If the service field is the differentiated services, the first 6 bits make up the code point subfield and the last 2 bits are not used. When the 3 rightmost bits are zeros, the 3 leftmost bits are interpreted the same as the precedence bits. When the 3 rightmost bits are not all zeros, the 6-bit defines 64 services based on the priority assignment by the Internet or local authorities. The total length field is a 16-bit field that defines the total length, which is header plus data, of the IP datagram in bytes. A 16-bit number can define a total length of up to 65,535. Identification, flags, and fragmentation offset are fields used in fragmentation, which will be discussed later. Due to some malfunctioning of routing protocols, a datagram may be circulating in the Internet, visiting some networks over and over without reaching the destination. This may create extra traffic in the Internet. The time to leave field is used to control the maximum number of hops visited by the datagram. When a source host sends the datagram, it stores a number in this field. This value is approximately 2 times the maximum number of routers between any two hosts. Each router that processes the datagram decrements this number by 1. If this value, after being decremented, is 0, the router discards the datagram. The protocol field is an 8-bit field that defines the higher level protocol that uses the services of the IPv4 layer. The checksum fields is for error checking of the header. The 32-bit source and destination address fields define the IP address of the source and destination respectively. The source host should know its IP address. The destination IP address is either known by the protocol that uses the service of IP or is provided by the DNS. The value of these fields must remain unchanged during the time the IP datagram travels from the source host to the destination host. A datagram header can have up to 40 bytes of options. Options can be used for network testing and debugging. Although options are not required part of the IP header, option processing is required of the IP software. Here are some of the options. A no operation is a 1-byte option used as a filler between options. The end of option is a 1-byte option used for padding at the end of the option field. The record route is used to record the internet routers that handle the datagram. The strict source route is used by the source to predetermine a route for the datagram as it travels through the internet. The loose source route is similar to the strict source route in which each router in the list must be visited, but the datagram can visit other routers as well. The timestamp is used to record the time of datagram processing by a router. A datagram can travel through different networks. Each router decapsulates the IP datagram from the frame it receives, processes it, and then encapsulates it in another frame. The format and size of the received frame depend on the protocol used by the physical network through which the frame has just traveled. The format and size of the sent frame depend on the protocol used by the physical network through which the frame is going to travel. For example, if a router connects a LAN to a WAN, it receives a frame in the LAN format and sends a frame in the WAN format. Each data link protocol has its own frame format in most protocol, where one of the fields defined in the format is the maximum size of the data field, the maximum transfer unit or maximum transmission unit or MTU. When a datagram is encapsulated in the frame, the total size of the frame must be less than the MTU, which is defined by the restrictions imposed by the hardware and software used. The value of the MTU differs from one physical network protocol to another. For example, the value for an Ethernet LAN is normally 1500 bytes, but for a WAN, it can be larger or smaller. In order to make the IP protocol independent of the physical layer, the designers decided to make the maximum length of the IP datagram equal to 65,535 bytes. This makes transmission more efficient if one day we use a link layer protocol with an MTU of this size. However, for other physical networks, we must divide the datagram to make it possible for it to pass through these networks. This is called fragmentation. The 16-bit identification field identifies a datagram originating from the source host. The combination of the identification and source IP address must uniquely define a datagram as it leaves the source host. To guarantee uniqueness, the IP protocol uses a counter to label the datagrams. The counter is initialized to a positive number. The 3-bit flags field defines 3 flags. The leftmost bit is reserved. The second bit is called the do not fragment bit. If its value is 1, the machine must not fragment the datagram. If it cannot pass the datagram through any physical network, it discards the datagram and sends an ICMP error message to the source host. If its value is 0, the datagram can be fragmented if necessary. The third bit is called the more fragment bit. If its value is 1, it means the datagram is not the last fragment. There are more fragments after this one. If its value is 0, it means this is the last or only fragment. The 13-bit fragmentation offset field shows the relative position of this fragment with respect to the whole datagram. It is the offset of the data in the original datagram measured in units of 8 bytes. Here is a sample fragmentation. The original packet starts at the client. The fragments are reassembled at the server. The value of the identification field is the same in all fragments, as is the value of the flags field, with the more bit set for all fragments except the last. Also, the value of the offset field for each fragment is shown. Note that although the fragments arrive out of order at the destination, they can be correctly reassembled. Internet Working Protocol version 6, also known as IPNG or Internet Working Protocol Next Generation, was developed to overcome deficiencies of IPv4. Address depletion is a long-term problem. Also, the Internet must accommodate real-time audio and video transmission. The Internet must also accommodate encryption and authentication of data. Here are the advantages of IPv6 over IPv4. Larger address space, better header format, new options, allowance for extension, support for resource allocation, and support for more security. The IPv6 packet is shown here. Each packet is composed of a base header followed by the payload. The base header occupies 40 bytes, whereas payload can be up to 65,535 bytes of information. The payload in IPv6 means a combination of 0 or more extension headers followed by the data from other protocols. In IPv6, options, which are part of the header in IPv4, are designed as extension headers. The payload can have as many extension headers as required by the situation. Each extension header has two mandatory fields, next header and the length. The 4-bit version field defines the version number of the IP. For IPv6, the value is 6. The 8-bit traffic class field is used to distinguish different payloads with different delivery requirements. It replaces the type of service field in IPv4. The flow label is a 20-bit field that is designed to provide special handling for a particular flow of data. A flow is a sequence of packets that share the same characteristics. The 2-byte payload length field defines the length of the IP datagram excluding the header. Note that the IPv4 defines two fields related to the length, header length and total length. In IPv6, the length of the base header is fixed. Only the length of the payload needs to be defined. The next header is an 8-bit field defining the type of the first extension header if present, or the type of the data that follows the base header in the datagram. This field is similar to the protocol field in IPv4. The 8-bit hop limit field serves the same purpose as the time to live field in the IPv4. The source address field is a 16-byte or 128-bit internet address that identifies the original source of the datagram. The destination address field is a 16-bit byte or 128-bit internet address that identifies the destination of the datagram. Here are some comparisons of the IPv4 and IPv6 headers. The header length field is eliminated in IPv6 because the length of the header is fixed in this version. The service type field is eliminated in IPv6. The priority or traffic class and the flow label fields together take over the function of the service type field. The total length field is eliminated in IPv6 and replaced by the payload length field. The identification, flag, and offset fields are eliminated from the base header in IPv6. They are included in the fragmentation extension header. The time to live field is called hop limit in IPv6. The protocol field is replaced by the next header field. The header checksum is eliminated because the checksum is provided by upper layer protocols. It is therefore not needed at this level. The option fields in IPv4 are implemented as extension headers in IPv6. Three strategies have been devised for transitioning from IPv4 to IPv6: dual stack, tunneling, and header translation. One or all of these three strategies can be implemented during the transition period. It is recommended that all hosts, before migrating completely to version 6, have a dual stack of protocols during the transition. In other words, a station must run IPv4 and IPv6 simultaneously until all the internet uses IPv6. To determine which version to use when sending a packet to a destination, the source host queries the DNS. If the DNS returns an IPv4 address, the source host sends an IPv4 packet. If the DNS returns an IPv6 address, the source host sends an IPv6 packet. Tunneling is a strategy used when two computers using IPv6 want to communicate with each other and the packet must pass through a region that uses IPv4. To pass through this region, the packet must have an IPv4 address, so the IPv6 packet is encapsulated in an IPv4 packet when it enters the region, and it leaves its capsule when it exits the region. It seems as if the IPv6 packet enters a tunnel at one end and emerges at the other end. Make it clear that the IPv4 packet is carrying an IPv6 packet as data. The protocol value is set to 41. Header translation is necessary when the majority of the internet has moved to IPv6, but some systems still use IPv4. The sender wants to use IPv6, but the receiver does not understand IPv6. Tunneling does not work in this situation because the packet must be in IPv4 format to be understood by the receiver. In this case, the header format must be totally changed through header translation. Here is the header translation procedure. The IPv6 map address is changed to an IPv4 address by extracting the rightmost 32 bits. The value of the IPv6 priority field is discarded. The type of service field in IPv4 is set to 0. The checksum for IPv4 is calculated and inserted in the corresponding field. The IPv6 flow label is ignored. Compatible extension headers are converted to options and inserted in the IPv4 header. Some may have to be dropped. The length of IPv4 header is calculated and inserted into the corresponding field. The total length of the IPv4 packet is calculated and inserted in the corresponding field. This ends Module 19. Thank you.